Okay, so hi everyone. Welcome to our second talk in the MuniHac track of Big Tech Day. And I'd like to welcome Christian Baaij as our next speaker. Christian's journey into Haskell started in 2009, quite a while ago, when he implemented the Clash compiler, a Haskell compiler from, well, a compiler from Haskell to hardware, together with another student. And since then, Christian has founded Cubase Logic, a company built on Clash and a company that builds custom FPGAs using Haskell. And also, Christian is known as the maintainer of various GHC plugins, in particular on type-level natural numbers. So, welcome, Christian, and enjoy the talk.
Thank you, Franz, for inviting me, and thank you all for attending. Yeah, a bit more about itself. So the co-founder part is explained. These days we're a bit bigger, and I actually get to focus more on the technical stuff. We've recently acquired a CEO who's taken a lot of my hands. That's really nice. Yeah, my passion is really circuit design. But also also Haskell. It's one of the reasons that I started Cubase Logic. I wanted a place where people could build both hardware and work on the software as well. That doesn't happen a lot, at least not in my part of the Netherlands. And I think sometimes people ask, like, what's a good way to start Haskell? And I would say, yeah, just build a compiler. It's worked well for me. You quickly get introduced to stuff like monads without really having to understand them. You just know which problems they take away, and you don't have to bother with all the fancy stuff. You just know, like, this is a nice thing to have. I'll just use that. Yeah, I work a lot on the Clash compiler, and just when I'm about to write awesome documentation for it, I start the game a lot. So documentation never happens, or I watch too much anime. Right. So about Cubase Logic. So Cubase Logic, our company builds custom FPGA solutions for our clients. We transfer the IP to our client, and I have to stand over here. Thanks. And an important part is that as a company, we are now stewards of let's say, the Clash project. Many of our employees, they contribute in some shape or form to the Clash ecosystem aside from doing client work. Because we are specialists, and in the type of fields that we work, we always have to work together with partners, and something we really enjoy. Just being able to build complex things. It requires a lot of knowledge from all kind of different fields. We just do the hardware part, or a specific part of the hardware part, and our partners do all the rest. So on the right-hand side, you see a couple of projects that we've worked on. The bottom right two are actually collaboration between us and some partners, and the top right two are actually also done all in Haskell. So that's I think it's pretty cool that we get to use Haskell in practice for these kind of systems where you might not expect Haskell, really embedded stuff. So one of the projects that I want to focus on that we worked on was this Tomcat project about optical laser communication in open space, in this case between a ground station and a satellite, where the basic idea is that the ground station sends a lot of data to a satellite, and then this satellite will distribute it to other satellites. So I guess in effect, like Starlink, if you think of the Starlink, you don't really care too much about the satellite sending a lot of data down. The feeder needs to send all of YouTube up into the air so that people can watch YouTube on their boat. So anyways, so that's the context for why we're building this terabit optical link. So it's again a consortium, lots of companies working together. It's led by TNO, which is let's say the Dutch equivalent of Fraunhofer, to give you a sense of what kind of company TNO is. So why would we want to try optical connections, open space optical connections in the first place? And we've been using RF for a very long time, but it turns out if you want to go to those terabit speed operations, it becomes very annoying. There's a lot of interference from other senders. You can, even though you can shape a radio beam, many people might think, oh, it's a radio is omnidirectional. These days, you have actually multiple antennas, and they sort of cancel each other out, so that you can actually shape the beam, shape your radio wave. It's still no way as narrow as a laser. And so with RF, you get a lot of, if you have two ground stations trying to communicate to two satellites, at some point they will interfere. You need to correct for this, and it's very hard to achieve your data rates. Also, there's always a problem with radio spectrum is that everybody wants to use it, especially on the ground, and so there's always a lot of competition for radio waves. And then maybe this is more for the military concern somewhat, it's easier to listen into radio waves than it is for optical links. So if you have an optical link, you have to be, first of all, extremely precise, because you need to be exactly in the laser beam, and then you need to do a lot of tricks to duplicate the signal, so it's not seen that it's being intercepted. Like you can't just cut it off, because then the satellite will notice the feed is gone. But it's all, so for laser, that would be another benefit. It's very point to point. It's very difficult to listen in. So, why haven't we done optical? Or, what's the big problem with open space optical communication? That's of course the Earth's atmosphere is really annoying. The air is very turbulent, and it causes refractions in the in the signal, and that means it's much harder to then recover your original image. Let's say we're just trying to see an image, but we've done telescopes for a long time, so in a way this is somewhat solved, and this is how they solve it. So let's say, well, it says there image disturbed by turbulence, right, by the atmosphere. So if you would view your light coming in as a wave, normally it would be straight, and then maybe there's something modulated on top. But the atmosphere disturbs it, so that's the optical image that we're getting. That goes into something called a deformable mirror, which is really just a segmented mirror that we can just very slightly adjust, and that actually corrects the atmospheric disturbances, and that would then be sent to the scientific camera that takes the long exposure. And we use something called a wavefront sensor to see basically the wiggles, how bad the wiggles are, is something that's being detected with this wavefront sensor. Actually, in our case, so the feeder link, we don't try to, we're not necessarily interested in correcting the image, the laser that we get back. We actually use it to improve the signal that we're trying to send back to the satellite. So the satellite is communicating with laser to us, but at a much lower frequency. We are now trying to send terabits towards it. And we use the same principle. So we see the deformation coming from using the wavefront sensor. And then we use the deformable mirror to actually pre-correct the laser. So we have a straight, we have a straight wavefront. Then the deformable mirror makes it all wobbly. And then actually the atmosphere corrects the wobble again, so that the laser receives the flat the flat waveform again. So how do we detect disturbances? Like how does it actually operate? So we have something called a Shack-Hartman, well, there's a mistake there, wavefront sensor. And so if we have a planar wavefront, which is the ideal one, if that falls into a lens array, then then it will focus the light exactly in the middle, so that's good. But if we have a deformed wavefront, the lenses will focus it slightly off-center, and that sort of determines the disturbance on the wavefront in 2D, and that's good enough for our purposes. So we together with one of the partners, we created a wavefront sensor. They were responsible for the optical part, creating like a 2D array of small lenslets. And another company was responsible for the CCD. But everything for terabit communication to work, the system had to work at 5 kilohertz. So the camera had to sample at 5,000 images per second. And then the control mechanism needs to adjust the mirrors, needs to be fast enough as well. And with these parameters, it was determined that it was okay to reach terabit per second throughput, because the atmospheric disturbance is not constant. But so with 5,000 kilohertz, it was sufficient. The air does not change too fast over the length between a satellite and a ground station. And in order to get this to work, we really needed to use an FPGA. And some of you might have heard this term, so I'll quickly go into what an FPGA is, and then I'll explain why we needed an FPGA. So an FPGA is not a standard chip. It's really a reconfigurable array of small logic blocks that can all be connected to one another with routers. Normally, you just set all of these routers once to compute the function that you want. And so if you then look at the top left, if you think about an FPGA, then you can have a lot of blocks that communicate directly with one another. Whereas a normal CPU and even GPU, but even if you have caches, you have to go back to memory. And if there's multiple processes trying to access the memory, there will always be contention on that memory. So you have to think about that up front. With FPGA, it's a lot easier. FPGA, you don't have to care about this contention because you're just communicating directly with your neighbor. You're not sharing any resource for the communication. So that's a really nice aspect about how FPGAs work. We just configure these logic blocks to perform our functionality, and they communicate directly with each other. But there are just so much more to it these days, to FPGAs, than this reconfigurable logic. They have all these embedded memories if you need to store something locally. We have complex DSPs or digital signal processing in there. And also currently, if you look at anything above 25 gigabit per second Ethernet processing, so 25, 50, 100, 400, if you want to do anything custom there, then FPGA is the only solution, because FPGAs have the transceivers to do this communication built in, and you don't have to go through PCIe, so there's no latency. You can just do the standard compute directly on your Ethernet stream, even at 400 gigabits per second. So FPGA is something quite different from either GPU or CPU now in how it works. And we needed that because for this application, we didn't really have a lot of time to do the processing. And it's not just about not having enough time, but also needing to be very, very exact. So for this wavefront processor, it makes no sense to calculate 5,000 images in the first 100 microseconds and then do nothing the rest. It's really about exact timing. We need, we start the exposure on the CCD, then the transfer happens, and we need to calculate almost immediately those differences from the center point. And ultimately, we're only allowed 3 microseconds after the final pixel came in. We need to complete the last slope. And there's no average frames per second. Like, there's no 99% or 99.9. We need to be accurate always. And it's very hard to do in most traditional CPU. If you have caches or it's out of order or a branch prediction, as a programmer, you would just be fighting it all. So we want a platform that makes it easy to meet these kind of timing requirements. So the next couple of slides are actually created by my co-founder of QA Logic, who was actually the main guy on this whole Tomcat project. So I wanted to, so that Jan, and I wanted to at least give him proper attributions for the things you're about to see. So so we need to do the image processing for the wavefront sensors. How will we go about that? So first we just want to build like a golden reference of how we're going to do the computation. And so how will we do that in Haskell? So let's say first, well, what are we trying to solve? So we have the full frame. Usually for the image, the edges are something we're not interested in, so we need to crop that. Then we need to figure out, so we need to identify all the sub areas where that would correspond to the lenslets. For the slides is 8 by 8, but in practice it was 16 by 16. Also, the lens doesn't focus just randomly. It focus in a region of interest, and this also allows us to filter out a lot of maybe other disturbances. We don't want to accidentally detect some speck of dust or something as as our focal point. So we only care about those regions of interest, and we can parameterize depending on the application. And then finally, once we have those regions of interest, we want to calculate the center of gravity, so where the focal point is of that lens, or where it focuses the laser light. So how will we go about it? So here is our region of interest. In this case, we have a matrix of 4 by 4 pixels. So how do we model our center of gravity? Well, we start out by summing all the rows. You can see the picture here. And then we multiply with the row coefficient, or the row number. And then we sum all that. And in addition, we sum the addition. So we've summed the columns and we've summed the row. So this is summing the rows. And then we divide those two numbers. And now we have the center of gravity in one direction. So this is, let's say, for the horizontal direction, this is let's say the diagram of doing the calculation. So this is what it will look like if you use a mathematical notation. And this is what it would look like if you were to write it in Haskell. And then there's a very one-to-one mapping from both the mathematics to the Haskell and the mathematics, or from the Haskell to the picture. So if you look at the fold, so we use fold left here, but that corresponds to this, chain summation. And then the map is because we've repeated it a couple of times, so that's, let's say, parallel composition of our functions. So if the zip width structure we see here in the circuit as well. So in this case, we have a vector of increasing numbers from 1, and the summation, and that we zip width together with the multiplication. And here we see again some folding structure. So there's really one-to-one mapping to higher order functions and let's say these kind of structures on the circuit. So this is the circuit just for one axis, so the horizontal one. And if we want to do the vertical done, we just need to transpose it and apply the same calculations. So that's what we see there. So how do we now get the regions of interest? So well, we start with a simple matrix. Then we select the rows that we're interested in, because we're not interested in the bottom and the top half. So the details are eluded here, so that's why the ellipse is there. But we just select the rows that we're interested in. Then we transpose, and we select again. So now we have the picture from the full frame, and then we transpose back, and we just have the picture as we wanted it. That gives us a matrix of A. And now if I want to split it into all of the regions that we're interested in, so that correspond to the lenslets, we just split it into n, in this case 4, so split it n ways, the picture. We transpose it, and then we map the split function, so we get all of the, basically we get over the columns, and as you can see, we get all these nice squares now. And then we need to transpose them back. So now we have a matrix of matrices. I think this is the nice part about Haskell is that you can really get a denotational representation of the problem that we're trying to tackle. There's no for loop, and you can really see nice step by step. So we try to, so now how does it look on our picture? We try to calculate the center of gravity. So we have our image. So we do the select 2D that just selects the picture or from the full frame. Then we split it into subsections. And then we just do a 2D map, which is map.map, over all of our lenslets. And we get our regions of interest. And then we map our center of gravity function to get the matrix of our centers of gravity. And I think, so what's really nice is that we get a very high level declarative specification of our problem. And it's, because it's Haskell, it's also executable, so there's a nice way of, so this is our golden reference. We can always communicate it with a client or some partner and just send it, and they can test it. Maybe they had some MATLAB model that they thought there was a good golden reference, but we can just then send them an executable, and they can compare. They don't have to install Haskell. They don't have to install tools. In principle, like the Haskell that we just saw, we could put it on the FPGA, but it would calculate all of the functions in. It would calculate all center of gravities in one clock cycle, but for this particular application, like a fully parallel implementation was not enough. I think it's funny when in Clash, when we're working doing circuit description in Haskell, the most naive implementation, the most declarative one, is actually also the most parallel one. And if we then want to if we want to realize it as a circuit, we want to make it more sequential. And I think that's somewhat, if you come from the software world, that feels perhaps unnatural, where you by default it is sequential, and I have to, decorate my code in many, many ways to make it as parallel as possible. But actually, so when you're in the circuit world, we start with a very parallel. Our high-level specifications are usually extremely parallel, somewhat too parallel, or the circuits become too big to fit on the FPGA, and we then have to decorate them to actually make them sequential again. We'll see that later. So going towards an FPGA, so the camera does not provide us the full frame, and I also showed you earlier, so the timelines don't allow us to wait for the full frame. We need to send, once we've calculated a slope, a correction for the top left lenslet, we need to send it to the control algorithm so it can already adjust part of the mirror. And so yeah, we get our image in packets of 12 pixels from one line every clock cycle. So basically, the specification that we saw earlier, that could process a whole frame, but we're not getting a whole frame. We're only getting 12 pixels at a time. So what we're gonna do is, we just need to build a simple state machine to track where we are basically in the image, and whether we are looking at the region of interest that we're interested in. So you don't have to follow this. I think it's more of basically you could give this to somebody who is just started in Haskell, and if you would explain them the problem, you're getting 12 pixels at a time and you need to track where you are, they would be able to write down this state machine. There's also another thing I want to highlight is that when you're working with circuits in Haskell, it's usually simple Haskell that you write. It's not too, and more the kind of Haskell that you might get in your first year of university. You would write something like this, but that's fine for our purposes. So this state machine basically controls, it determines, are we looking at the region of interest, and that will then later feed into the circuit that does the center of gravity calculations. Yeah, some of the data types. So there's no package. So we have a package data type that defines that we have no package, because actually the FPGA runs almost 2.5 times as fast as the camera. So sometimes we get image data around every 2.5 cycles, and so sometimes 2, sometimes 3. And yeah, it determines did we start a frame and are we at the end of frame? So those are the 2 booleans, and then we get a vector of 8. So those are the those are the 8 pixels, and the pixels have a 12-bit value. So there's a bit of fancy Haskell in terms that we have the numerics at the type level, but that's about the fanciest as you get. If you look at let's say the term level part, it's very Haskell 98. And again, also the state machine, it's just a simple sum product type, or it's just a sum product type to define the state machine. Yeah, so the circuit the specification that we saw earlier, did it for the full frame, but that's too much for our purposes because we're only getting 8 pixels at a time. So we're gonna try and make the circuit smaller, or as small as we need it to, because if it's smaller, it uses less energy. Also, in many cases, it means we can run it much easier at the target frequency. In our case, 250 megahertz. So making the circuit smaller, doing things sequential is often better. So we just focus at the numerator. And this is the fully parallel implementation that we see here on the left. But we can, so the fold on the right, that's currently, on the left-hand side, you can see it's happening in space. It's happening instantaneously. But if we want to transform that so we accumulate over time. And so on the right, you can see the structure that corresponds to. We have that box there that's called a register. It's just a very basic memory element that will store our accumulated value. And so instead of folding in space, we fold over time. We accumulate the value over time. So there we see the register function that corresponds to that block that you see in the diagram. So that accumulates the value over time instead of in space. And then, so we do one more transformation. Basically, because we have so much time, we get 8 pixels in a row, And remember, the center of gravity is both in the horizontal axis and in the vertical axis. We needed to do the center of gravity calculation. We actually want to reuse part of the circuit. So if you look on the left-hand side, so that we see the multiplication that happens on the end, but we can also distribute it over the entire fold. And you might think like, well, now we have more multipliers, it's more expensive. But that we did that, so that might be true for, let's say, if you just want to do the horizontal axis. But for the transposed version, that I is, for the transposed version, if you want to do it at the same time, you want to provide the consecutive numbers. So if you look at the top, we get, you know, the 4 pixels and then this I. In the horizontal axis, that would just be, you know, constants 1 or constants 2, depending on which row we are. But for the column 1, those I's would be consecutive numbers. So, you know, 1, 2, 3, 4 or 2, 3, 4, 5, depending on where we are looking in the region. So now we have one circuit that can, you know, in first instance be used for accumulating in the horizontal and then in the vertical. And we can share the structure. And actually, so this is just for the numerator. For the denominator, we have a similar structure. So then the I is just a constant 1. So here's a small, you know, graphical representation of how the circuit would eventually work. I think so. At the bottom, you get the center of gravity, and above that. Slightly above that, you see this array of values, right? So those values, that array corresponds to the center of gravities for one row, basically, where the first row of that matrix corresponds to the accumulated value of the numerator in the horizontal direction. Then the second row corresponds to the accumulated value in all the vertical directions, and then the bottom row is the accumulated value of the denominator of the division. Well, then the circuit runs, and it will fill this whole table with values. And eventually at the end we'll get some values out at the bottom. So we've written all of our Haskell, and now we have a nice specification. I think what's also nice is that we can play with numerics. So we might move to fixed point, for example, and we can, because it's all Haskell, we can ship it to our client as well, so they can test against some very specific fixed point representation instead of floating point, and see if it still works for their application. But so regardless, we have our Haskell program, and now we feed that into the Clash compiler, which is actually it takes a lot of the Haskell infrastructure. It takes a lot of the GHC Haskell compiler as a front end. It uses that for a lot of the parts of parsing, type checking. So Clash really only takes the semantic subset of Haskell, and that translates that to languages like VHDL or Verilog, which are languages that are the standard FPGA tools understand. And then from those VHDL and Verilog files, we generate the bit stream that you use to configure the FPGA. So then in terms of the results, so yeah, the state machine and the center of gravity calculations, because we only needed one, the way the camera only provided 8 pixels at a time. We only used 2% of the entire FPGA. We achieved a clock frequency of 250 megahertz. You might think this is very slow compared to modern CPUs, but let's just say that this part, the Zinc 7000 part, I think the fastest it can run is 400 megahertz, so being at 250 is not too bad. And also in general FPGAs, the fastest they can run is 800 megahertz or 900. but they do a lot of, they make up for that for doing a lot in parallel. So they can still process a lot of data. So yeah, also I didn't really show you this, but those operations, the multiplications, they run on floating points, so they're actually pipelined. So that means that once we get the final 8 pixels, it still takes 20 clock cycles before we provide the center of gravity. But so that's 100 nanoseconds after we get the last pixel values. 100 nanoseconds later, we provide the center of gravity for the final region of interest. And we needed to reach 300 microseconds. So let's say, on average, we were basically 300 microseconds earlier than we were supposed to be at 100 nanoseconds. Yeah, I think, so we did all of this work in, let's say, 2019. And it took some time for all the other parties to come together. But finally, in September of last year, there was a successful field test. So on the bottom left, you can see the feeder station. So the ground station is quite big. I don't know whether you can see the wheels, but yeah, it's probably in the side of that thing is as big as this screen. And then, so that was on the ground. And in some tower, there was the satellite part, or part that would go in the satellite. And they were tested at 10 kilometers, and they did a ground-to-ground link. And 10 kilometers ground to ground, the turbulence actually way worse closer you get to the Earth. So that's comparable, you know, that gives us comparable conditions if we were to do from the ground to a satellite and maybe 139 kilometers. So 10 kilometers. And we were able to successfully get, at this point, 25 gigabits per channel. And so you might think, yeah, that's still far away from the 1 terabit, but originally the idea was also to use multiple wavelengths to begin with. So we will have multiple wavelengths in our laser, and each carrying in 25 gigabits, or probably will be a bit higher eventually. So even though we're, let's say, 2 orders of magnitude out, we will get there at the end with multiple channels. So I guess, like, what I hope you take away from this talk is that, you know, for certain situations, they might seem very difficult if you've never heard of an FPGA. But basically, if you have, you know, hard real-time constraints, if you really need to deliver something exactly every 3 microseconds, or if you have very low latency. So FPGAs, for example, are used a lot in algorithmic trading on the market. So if you can beat your competitor, so if you can give your answer faster, then you use FPGAs. Although these days the FPGA is no longer the determining factor for high frequency traders. It's the radio wave towers, because that's you get more speed up from sending radio waves in a straight line than using a cable that tracks the curvature of the Earth. And also the medium is better. So actually light travels faster over the radio waves than the light in the cable. And that matters over distances like New York, Chicago. Yeah, if you have very high bandwidth, or like, for example, in the space application, so we needed to do a lot of compute in low power. Eventually we want to get this thing on the satellite as well, maybe not the same, but not terabits. And then you know, you want to, in space, you don't want a lot of heat because it's difficult. There's no medium to radiate it out into. All you get is basically, the only way to radiate heat is infrared, which is not the best. Another thing, maybe if you're more in the embedded side, eventually maybe your microcontroller runs out of peripherals it can talk to, because it only has, you know, 12, or it only has 5 I2C peripherals. With FPGA, you can talk to like hundreds at the same time. So that's another reason to use FPGA. I think, so about Haskell and Clash is that what's really nice and that's difficult to achieve in let's say more traditional approaches, that we get both a very high level model that's executable that we can send to a client, and also a very detailed implementation that has good performance, but we can also turn into an executable and send to the client. So again, like I said, if we want to do some fancy numeric stuff and maybe we introduce errors compared to floating point, and in this case it matters in which order you do the operations, the error you get. So the implementation really matters then. The implementation details will really matter for the numeric stability. And so we can send an executable of that towards the client and they can test it, and it's really powerful. And I think, so the final takeaway is that, if you want to write high performance Haskell, it can be simple Haskell. Just at the small fancy types, but a lot of the code, the term level stuff that you write is really just the type of Haskell that you probably fell in love with when you did your university course or saw Haskell for the first time. You probably didn't fall in love with monads. You fall in love with a nice declarative Haskell, and that's what circuit Haskell is. So if you want to start with Clash, you can go to this website, and there's also a nice book. You can build retro computers with Clash as well. There's a really nice book, and if you're familiar with Haskell a bit, then we'll just start with that. Thank you. That was it.
All right, thank you so much, Christian. Are there any questions? Yes, I see the first one here already.
Hi, so I assume you have many optimizations which are only applicable to the FPGA use case when you convert GHC core to your intermediate representation or such. So about the GHC's own optimizations, do you find them in practice to be actually useful, or do they have an impact in the final quality of the FPGA that you generate?
There are some, so in order to get the Haskell to perform well on sequential machines, worker wrapper is very important, and worker wrapper has no effect for us, and it's just mostly annoying if the worker wrapper transformation is performed. So actually we try to avoid it. It doesn't necessarily make the circuit worse, it just makes the compile time for Haskell to circuit longer. And then, I don't know, I think, so GHC CSE might be a bit better than our naive common expression elimination. So we do use some of the transformations. I'm trying to think, I don't think in terms of performance it really matters, the optimization that GHC applies. Well, we found it actually that just turning on the optimizations does actually improve the circuit and not make them detrimental.
So I have a hardware question. It sounds like the limiting factor to the update time of your system is the camera performance.
Mm-hmm.
Have you thought about using cameras that maybe read the image in an interlaced way instead of from top to bottom? Is this something that even exists?
Oh, you mean the readout of the camera link? I think, so for this application it was fast enough, but maybe for like even higher update frequencies, you might not get away with just line by line readout. I don't have a good answer for that. Sorry.
Thank you for the talk. Do you ever have the need to formally verify the software that runs on your FPGAs? And if so, programming it with Haskell, did it have any meaningful impact on that front?
No, so far we haven't had a need for formal verification. I think if you look at the safety industry in practice, formal verification is not a thing. Even in automotive, it's more about somebody from some fancy firm comes by and checks that you have good guidelines in place, or you're using a compiler that has been okayed for use in in automotive. You can't use anything else. So far, we haven't done any formal verification. I think, and even then, if we wanted to do formal verification, then Haskell is not the right language right now, because Haskell does not have a formal semantics. Not in the way that we can that you can reason about it inductively. You get bottoms everywhere. You would have to use more like a language like Agda, so that you get termination to be able to prove things in the system itself. So that's one part, and then going to a circuit is another part. Because Haskell has no formal semantics, well, we can sort of have to define one, and then just hope the world agrees on the formal semantics, and then we need to prove it inside every step. But then our target language, which is Verilog, also does not have formal semantics. There we also just have to pick a semantics and hope the rest of the world agrees on that semantics. So we're just not in a great place for formal verification.
So you did matrix multiplication, basically, or matrix analysis.
Yeah.
That doesn't sound so complicated. That I think people do this all the time in Verilog or VHDL.
Mm-hmm.
So can you compare? Like, do you have a reference implementation in the other languages that have like significant drawbacks that show that in this case Haskell was really the better way to program this? Other than, the high-level program as a reference, maybe?
So I think for this particular case, it was, maybe we could have done it directly in Verilog, but it's to do the complete derivation from the high level to the detailed implementation, to do that in one language. That would be kind of annoying to do in Verilog. So for us, that's where Haskell paid off. And like if we would have to do this in Verilog, then you'd have to basically scour the internet, hoping to find a package that does the thing that we want. Because you say like, well, it's matrix manipulations, but in the hardware world, like libraries are not really a thing, and that the hardware world is, I guess, more. I was talking to somebody yesterday, and that would be more compared to Java, where you have some standard library, and then everything is closed source. And it's the same for the hardware world. It's very difficult to find, more specific libraries.
Yes. So first, thank you for the talk. I've never written a program in FPGA before, so maybe my question is naive. How does the Haskell code interact with the peripherals? So usually when I program a microcontroller, I have some way to have memory mapped I/O, and then I can read stuff from there, but I guess it's not directly possible in Haskell.
Mm-hmm.
So how does the interaction from Haskell to the peripherals or outside world work?
Yeah. I think, so the way that works is that basically the data that the peripheral sends to the FPGA, they just become an argument to your function, and any data that you want to send back to to the peripheral. It's just the result. So if you have a lot of peripherals, then you compose them all so that your top-level function will have then a lot of arguments and a lot of results. So in an I/O system, that would be sort of hidden because you're talking to some memory you're talking to some memory, and that sort of abstracts away the communication. And this being more of a pure functional sense, if you need to talk, you basically need to pipe down your arguments all the way from the top and then pipe back up the results to them. But there are ways that don't make this too uncomfortable in terms of how you write it.
Thank you. I have two related questions. You had a slide with, say, cascading time delays. I was wondering, do you measure them from the real hardware, or do you have some sort of simulator that you use for development? And my second question is, how consistent would you say are the timings in the real world?
So the delays that I showed, that was in terms of modeling. So for every part of the algorithm, we were allowed a number of time and when we were supposed to start. So that's why I showed the picture with the delays. And that just was more to show that, we needed to start as soon as we got the first pixel, and when the last pixel comes in, we only had 3 microseconds to deliver the results. And we couldn't wait. So we had to both immediately start delivering the results, and the last result needed to be delivered at 3 microseconds. So then coming back about how accurate it is. So the FPGA itself, so it's fully deterministic in terms of clock cycles. So really, the moment we would get the last pixel, then really 20 clock cycles later, we would produce the results, which would equate to 100 nanoseconds in this case. So the thing that drives the clock signal, it does have some perturbations, but usually they are in the parts per million. So might be femtoseconds or picoseconds off. Picoseconds would be really bad. And so in that you're quite accurate. So maybe the CCD, so maybe there's so we would, the jitter that you might get, for example, is on the order of 4 nanoseconds, because our FPGA does something every 4 nanoseconds, but the data might not be exactly at the point that we need it. So we would see it 4 nanoseconds later. So perhaps frame to frame or line to line, we might have a jitter of 4 nanoseconds.
All right, are there any more questions? Yes.
Maybe a bit unrelated, but how do you deal with absorption? So you talked about distortion, but what about clouds?
I wouldn't know actually. I think we used it, so it's a 50 watt laser, so it's high power.
So it goes through the...
And I think they might use, I don't know what frequency they use, but I really need to, it was one of the questions I had as well, to be honest. But I think they might use frequencies that are not absorbed. Yeah.
Okay, are there any other questions? If not, then give Christian another hand. Thank you very much.